to mechanism design. Today's topic is going to be linkage mechanism velocity analysis. So let me all right. So we have started last time the lecture on this linkage velocity analysis. So for example, if we have this one ternary member ABC, which is rotating counterclockwise about point A. So you see the velocity can be divided into two components. One is the linear velocity, which is straight lines. And then next is the rotational velocity or angular velocity. So which is shown by this curved arrow. So you can rotate in any of the two directions, counterclockwise or clockwise. Usually the linear velocity is measured in meter per second, feet per minute, or FPM, or miles per hour, or kilometers per hour. Whereas for the angular velocity, we usually measure it in revolution per minute, or RPM, or RPS, radian per second, in some situation degrees per second. So again, the direction of rotation is positive in the counterclockwise direction, whereas if it is rotating in the clockwise direction, is considered as negative rotation. So omega is the differentiation of the angle with respect to time. Sometimes it is shown as theta dot, but in this class, the notation that we are going to use is omega, which looks like a W. So the relationship between linear velocity and angular velocity is shown as in this example, V equals R omega. So we will see in this equation, usually we will want the omega to be in radian per second, and that R can be in either inches or in meter, and the resulting velocity unit will be in accordance to whatever unit used in R and also omega. So example one is shown, and already went through it in the class. So here we have the linear velocity, and as you can see, actually the linear velocities are perpendicular to their respective link. Okay, so the link is actually the straight line between the one end to the other one, between the tail and the head, or the tip of the link. So in this case, between A and C, so VC must be perpendicular or 90 degrees, whereas VB is perpendicular to RAB, or the link A to B. So from here, actually, if the given information is VC, so from there we can solve for the omega, and it's going to be the same omega since A, C, and B are actually in the same body, even if it is mixed or is made from two binary links, but they are joined together or welded together at about this position. So whenever they rotate, they will rotate in the same omega. So the situation is worsened if or becoming more challenging if it is a 4-bar mechanism. Here we do not have only one body, we have at least 3 bodies that are moving or rotating, and one body which is the ground being fixed. All right, so again, the known information or the input velocity is VB, or maybe even it is actually given by omega 2. So if we have omega 2 and we know perhaps we know the or R2 and omega 2, so we can solve for VB. We can calculate VB. And the other velocities are actually unknown, so we need to be able to solve these two unknown velocities, which is VC and also VCB. And those are perpendicular to their respective link. So VCD is or VC is perpendicular to R4, whereas VCB is perpendicular to R3. So we do not know whether VCB is going to point this way or the other one, opposite direction. And same for VCD, either it is pointing this way or that way. So what is important is for us to know that VB is a absolute velocity that is connected or related to point A, and point A is on the ground or a fixed pivot. Same as in VC is with respect to point D, and point D is connected to the ground. So this is a fixed pivot. So meaning VC is absolute. Whereas for VCB is relative velocity of point C relative to or related to as measured from point B. Okay, so the origin is at the tail of VB, and actually in terms of labeling in the vector polygon, the velocity polygon, point A and D has to pass through this origin, origin OV. So that's why VCD, since it is related to the fixed pivot, so it needs to pass through this origin OV, whereas VCB is not, is relative between point B and C and B, and needs to pass point B in the velocity polygon. So from there we can get the intersection to get point C. Okay, and then we just finish up the two vectors, and now we know completely, you know, the direction as well as the magnitude. So take for example this offset slider crank example. Okay, we have the crank at point 2, member 2, and link 3 is the connecting rod, slider at the 4, and we have this offset. And then we have this VB pointing that way, and we can calculate VB as shown over here, and we can label it like that. And then we got to understand a few more things. So like the velocity, there'll be velocity that is perpendicular to the connecting rod, and also there's a velocity for the slider. So for the slider, it's not going to be perpendicular. It is along the same route of the slider. So that's a different thing because the slider is not actually rotating. It's sliding along, in this case, straight line. So from there we can know this is the known VB is the known velocity, and the tail is where OV is, and point AD are located at that position as well. And then this line VCB will pass through point B, whereas point velocity for the slider will pass this origin, and from there we can get the intersection for point C. Okay, and yeah, so this is the solution using graphical method. Graphical method, either you want to draw manually, but you need to get very accurate, as well as you can use AutoCAD or any other CAD. So this is trying to solve this thing analytically using vector method. So first of all, you need to come up with the loop equation. So we have R2 here plus R3 equals to R1 plus R4. So you can rearrange stuff and you get something like this, and you notice you know everything on the left hand side, and you got 8.66 and 12.5. And then you need to look at the top row as well as the bottom row, see which row that we need to use first to be able to solve at least one of the variable or one of the unknown first. In this case, we can solve for theta 3 using the bottom line, bottom row, and then plug in this information. We get theta 3 to be a negative 18.21. And definitely from this sketch, our theta 3 is in this clockwise direction, and this mean is supposed to be negative. So 18.21 seems to be correct. The other option that we can get is 180 minus this value. So it'll be like 200.21, something like that, close to that. And it is going to be pointing this way. So the same theta R2 at 30 degrees. So you can get theta 3 pointing that way. Okay. Or R3 pointing this way. So that's the second possible solution, which is incorrect. So according to this sketch, we need the theta 3 to be a negative number. So that is correct. And then once you get that settled, you can plug in the top row the value of theta 3, and then we can solve for R4, which gets you 46.66. So if you refer to this AutoCAD drawing, R4 is 46.66, and our theta 3 is 18.21, and that's actually a negative value. All right, so similarly, if you are solving this purely using the vector method, you do not have access to CAD or maybe drawing manually. So you can set it up in this manner, and then take derivative with respect to time, and you get R will be same here. Okay, and then cosine theta 2 will be sine theta 2. Sine theta 2 will be cosine. And then you differentiate the theta 2 itself, and you get theta 2 dot. And in this case, we have omega 2 instead. Then you do the same for this one and this one. So for R4, you differentiate since R4 is not fixed, so you get V4. Then what you'll do is rearrange. You can get it in this formation, and then you can use solve this thing like a matrix system. All right. Okay, so next we are going to have this 4-bar example, and I'll leave that for the next class. And stop the sharing. And should you have any problem, feel free to contact me regarding this topic. In the meantime, I will supply you in ULearn the homework assignments 1 and 2, so that you can practice on the topic of the basic of mechanism or kinematics, as well as a little bit on the position analysis and velocity analysis. So perhaps by next week we can do the acceleration analysis. With that, thank you very much for your attention. Hope to see you soon in the next class. And we'll continue this journey on mechanism design together. Assalamu alaikum. Have a good one.